So now what about the case where you have multiple switches together connected to each other? This is obviously a very common configuration in any large enterprise where you can have switches in multiple buildings, but you're going to have everybody on the same subnet, so the switches are connected out to each other. So basically the same thing applies. So you're going to basically say for example, you have to send a message from A to G, and that's going to go through switch 1, switch 4, and switch 3. So what's going to happen is you start off with A, says I want to get to G. Switch 1 does not know where to go with that, so it's going to flood all its ports. It's going to get received by switch 4, and switch 4 is going to flood all of its ports, which will include switch 3, and the switch 3 may or may not know about G. If it does, it'll flood it with G. G will eventually respond, and eventually switch 1 will get that. We'll get host G in this routing table saying it has to go out this port, whatever that number is. So as you can see, switches are a lot easier to work with than routers, because most of the work that the router does, where you have to have a lot of configuration management, the switches do basically on their own. They're a little more simpler, but they do have some things in common, and sometimes people get confused. So basically, it's very important to understand the difference. It's also important to understand that from a product point of view, there are lots of products that do both switching and routing. But basically, switches and routers are both store and forward devices. The routers do that storing and forwarding on the network layer. They're looking at the network layer headers, where a switch is a link layer device, so it's looking at the link layer headers. They both have forwarding tables. Routers have to compute the tables using routing algorithms and IP addresses. Also, to complicate things, you have to deal with, IP subnets, and routers are also getting, longer vectors of, source to destination information, where switches just care about local connections. And switches, their forwarding tables are learned basically using flooding and self-learning, and they're basically storing the MAC addresses in their forwarding tables as opposed to the router. We're storing IP addresses or IP subnets. Okay, next let's talk about the concept of a VLAN or virtual LAN. So in our discussion of virtual LANs, I think the one thing that we really need to keep in mind is basically what we talked about when you bring your move a host from one location to another. You bring that MAC address with you, but you have to change IP addresses. So we want to kind of be able to kind of manipulate that a little bit. Maybe move around our hosts and have some flexibility with that. So let's take a look at this example. So imagine you have a university campus, and basically has different buildings. It has a computer science building, electrical engineering building, a computer engineering building. Each of them have their own local area network. They're tied to the main university switch, so they can have access to some servers. Maybe this is a switch router. We don't know. Maybe this is the router that gets us out to the outside world. And basically you have a person, for whatever reason, teaches in the computer science department, but their office gets moved to the electrical engineering building, but they still want to connect to the computer science switch. So that means that all the layer 2 broadcast traffic um, that host would need to have access to has to traverse across this entire land. We may or may not want to do that. So we use the concept of virtual LANs. So like I said, sometimes what we may have to do is because the assumption is this particular user is going to talk directly with other hosts and in that computer science network. Maybe they're setting up things in the lab here where they're doing setting up their own little client server data distribution type things here. So there'll be a lot of layer 2 traffic, and now we have to send this layer 2 traffic across this whole part of the network instead of just the computer science section. But we want to have the flexibility to do that. So we go into using what are called virtual LANs. So now, rather than having LANs that are location dependent like a particular building, we can have location independent networks. So we can have, say, the marketing LAN be all over a particular building or all over a campus. We can set it up so a user can move but not change the local area network that they are connected on. This use of VLANs is usually used when LANs are routed, so that the LANs are assumed to be on different subnets. And so this allows you to still keep that inner LAN traffic in one subnet rather than having to flatten out the whole organization. It also provides better security, and that's that kind of assumes that somebody in a particular organization is going to kind of snoop on another part of the organization. So this really doesn't really apply that much, but it does allow you to separate data flows into different need-to-know areas. So what this basically does is it takes our Ethernet switches and it basically gives them another capability. So basically what it does, virtual LAN support does, is it let switches that have a VLAN capability be configured to define multiple LANs over a single infrastructure. So basically, imagine you have a switch and you have the folks connected from ports 1 through 8 are in the electrical engineering department. Folks plugged into ports 9 through 16 are in the computer science department. So now you can, even though these are all on one switch, you can treat them like they're on two separate switches. You can keep the ARP traffic local to these ports. You can give these guys a different IP address. And usually, to be honest with you, a switch that supports virtual LANs also has a routing capability, so we can actually treat these as two separate subnets, and we can actually route the IP addresses between them. So we have a lot of capabilities. So what do we get from this port-based VLAN? Well, basically we have traffic isolation. So frames to and from port 1 through 8 can only be reached from port 1 through 8. We can also define VLANs based on MAC addresses of endpoints rather than switch ports, which gets a little hairy. We try to stay away from that. So basically what this means now when I'm broadcasting, an ARP address, I'm just going to keep it on the blue ports and rather than over all the ports on my switch. So I'm isolating my traffic a little bit. You have dynamic membership. Ports can dynamically be assigned amongst VLAN, so this guy over here can change from being part of electrical engineering to the computer science VLAN. And forwarding between VLANs is basically done via routing, just with separate switches. So like I said, usually a switch that supports virtual LANs also have a routing capability. So they're really switch routers. So VLANs can span multiple switches, and we use that by defining a trunk port. So the trunk port does not have any hosts on it. It basically has, it's a switch-to-switch connection, and it basically carries the frames between the VLANs over multiple physical switches. So the frames that are forwarded within a VLAN, VLAN can't be vanilla 802.1 frames. They have to carry a VLAN ID information so you can differentiate. So we basically use the 802.1q protocol to add these header fields for frames that are forwarded between trunk ports. So we're going to talk a little bit about what the 802.1q VLAN frame format looks like. So what we do here is we're basically at this point of demarcation we're adding some additional fields between the source address and the type field. So basically we're going to start off with a 2-byte tag protocol identifier. So when the switch is looking at a frame, when it sees this value, it knows, okay, that this is going to be a VLAN frame and not a regular 802.1 frame. Then after that protocol identifier, it's going to have the control information. It's going to have a 12-bit VLAN ID and a priority field similar to the IP type of service. We're not going to cover that in any great detail. But basically these are added to differentiate this one to identify this as a VLAN frame and this to provide the actual VLAN ID. So to describe that in greater detail, so like I said, the tag protocol identifier is a 16-bit field. It always has this particular value in order to identify the frame as an 802.1q tagged frame instead of a regular 802.1 frame. It has tag control information, the priority code point. That's a 3-bit field which you can look up in the 802.1p class of service. It maps to the frame priority level, value or priority or background, best effort, excellent effort, critical application, up to 7 network control. So these values can be used to prioritize different classes of traffic. So hopefully when we get to talking about quality of service later on in this course, we will talk more about these types of items. And then finally, we put our VLAN identifier into the VLAN identifier field. Now basically this concludes our lectures on the link layer. We basically covered everything that I felt was important for us to go on for the rest of the class. This also concludes our review. The next set of lectures in this particular learning module is on the physical layer, which we did not cover in 475. The physical layer also is not in the book for this class, but actually it is in the book that we use for 475. So we'll be covering that in the next set of lectures. Thank you.